Getting a custom-built carbon fiber quadcopter to hover perfectly in midair is an incredible feeling of true aerospace engineering. But getting to that point requires taking a pile of raw carbon plates, loose wires, and bare electronics and assembling them into a flight-ready machine. Before starting, you need 4 core hardware components: a frame kit, a set of brushless motors, a central flight controller, and a high-discharge LiPo battery. You will also need a basic set of hex drivers and a soldering iron and web access to the spdrone hanger configurator. Following a strict aerospace methodology during construction is the only reliable way to prevent catastrophic mid-air failures and ensure your custom platform actually flies. The first step happens before you touch any physical hardware. Open the hanger configurator and select your intended components from the interactive menus. This calculates the all-up weight, or AUW, the exact total mass of your drone, including frame, electronics, and battery. This mass dictates the mechanical lift your motors must generate. For safe flight, your thrust must be at least double your weight. Planning these weights and ratios digitally prevents a very common beginner mistake: purchasing mismatched motors that are ultimately too weak for the payload. With the math verified, move to the physical workspace. Start by aligning the carbon fiber drone arms with the central chassis plates. Secure these rigid carbon fiber layups together using the provided aviation-grade alloy hardware. As you insert these fasteners, be extremely careful to avoid over-tightening the screws directly into the carbon material. Applying excessive torque without a calibrated driver crushes the internal weave of the carbon fiber. This creates microscopic stress fractures that you cannot see with the naked eye. Treating the carbon fiber with precise structural discipline guarantees your frame will survive high-G maneuvers without shattering under the pressure. Next, install the 4 brushless motors at the extreme ends of your newly assembled carbon arms. Strip the motor leads, solder them directly to the electronic speed controllers, and wire those ESCs straight into your central PX4 flight controller. Pay close attention during this step. The primary integration failure point is accidentally reversing the motor spin directions during wiring. This diagram shows the exact layout required to achieve balanced lift. You must wire the system so that 2 diagonal motors spin clockwise and the opposite 2 spin counterclockwise. Finish the physical integration by securely strapping your premium LiPo battery to the frame and plugging it into the main harness. Flawless electronic wiring and correct rotational layouts are what ultimately translate your digital flight commands into stable physical movement. Power on the drone. Your focus now shifts away from the physical hardware and onto the digital ground control station. Open the telemetry black box interface. This dashboard displays the live diagnostic feed, confirming an active system status, your current battery voltage at 22.8 volts, and a solid 16 satellite GPS lock. But the single most crucial metric for wireless safety is the Received Signal Strength Indicator, or RSSI. Check the RSSI value on your dashboard. You must verify a signal of -50 decibel milliwatts or better before proceeding any further. Confirming healthy telemetry data before the propellers ever spin acts as your ultimate failsafe against mid-air signal loss and runaway drones. Before flying, complete one mandatory safety phase. Connect your RC controller directly to the website simulator. This graphic shows a 2D physics-based simulation on the left mapped directly to your physical RC stick inputs on the right. Use this environment to test your thrust vectoring and confirm that the physical motors will respond identically in the real world. With a digital checkout complete, you can confidently transition to the practical flying field for the maiden voyage. Mastering this workflow, from weight calculations and structural assembly to signal validation, ensures the final machine is a reliable flight platform that performs exactly as you designed it.